So I don't know, maybe I should just start. I won't wait for any higher authority. So first thing I'd like to do is to tie up a loose end from the last lecture. So this is a definition I really should have made last time. So let's say that x is smooth and projective. Then x is minimal if it contains no minus 1 curves. This implies that there does not exist a morphism phi to x birational to a smooth projective variety. The reason is that in our analysis of birational morphisms, in our classification, we've shown that all birational morphisms are sequences of blowdowns along minus 1 curves. So if there are no minus 1 curves, then there's no way to do this. So another way to think of a rational surface is that it has no birational morphisms onto simpler surfaces. It's important here that we have smooth. There are lots of maps from a minimal surface to a singular surface. That doesn't affect the minimality. So, I'm sorry? Okay, phi, birational, not isomorphism. So, what I'd like to turn to now is the geometry of effective divisors. And how this leads to classification results. So basically the idea here, which we've seen in special cases last time, is that so the presence of minus 1 curves depends on interaction between the effective divisors and the canonical class. So I'm going to describe how the effective divisors and the canonical class interact with each other. So for the time being, let's assume that x is just a smooth projective variety of arbitrary dimension. One reason for doing this is that divisors in curves behave in general quite differently from each other. And it's a good idea to maintain good mental hygiene when you're analyzing divisors and curves. When you're thinking about something as a divisor, you should use a notation and the constructions appropriate to divisors. If you're thinking about something as a curve, you should use the constructions and notation appropriate for curves. For surfaces, divisors and curves are the same, but you still need to maintain the requisite mental hygiene. And it will also be useful because a lot of the formalism will be used in Professor Tinkle's lectures on height functions and height theta functions. So let me introduce some notation. So I have the homology group, H2 sub z, and inside of this I have the sublattice corresponding to homology classes of curves in X. So inside of here we have the monoid of effective curves. this is, I'm going to write it like this. So this just consists of those classes such that D is an effective in the sense that D is a sum of irreducible curves with non-negative coefficients. And this is a monoid because I can add any two of these together. We also have the associated cone. So this is called the pseudo-effective cone. So this is a cone in the real group here. So this is just obtained by extension of scalars. And this is the smallest closed cone containing our monoid. So the picture is that if I have a monoid generated by two divisors, say D1 and D2, the cone, wondering how I can avoid that. The cone is just the cone determined by these, the cone spanned by the corresponding generating elements. This pseudo weasel word, this qualification, is because in general, there may be things at the boundary of this which are not actually represented by effective divisors. In our situation, we won't come across that because we're focusing on rational varieties. In fact, we're focusing on mostly del Pesto surfaces. But in general, this may have lattice vectors that are not represented by effective divisors. So let me just make one other definition. So a divisor D on X is NAF. Okay, I don't actually know what NAF means, and there's some controversy. Some people say it's numerically eventually free. Some people say it's numerically effective. I think there's some argument about it. And the way to diffuse the argument is NAF is just NAF. It's an acronym that doesn't actually mean anything. So this is so a divisor is NAF if when I intersect this with any curve C, this is non-negative. This is for any curve C in X. Now, we also have, so if the Néron-Severi lattice inside of H upper 2 and I can look at the NEF cone inside of the corresponding real space. This is just the smallest closed cone containing all the NEF divisors. And I guess I should also introduce notation for the interior. So this is the interior of the cone of curves. And here we also have so this is the interior. An important theorem due to Kleiman, which I'm going to I'm not going to prove this, is that, in fact, the interior of the NF cone is just the ample cone of X. So the picture you should have, so if I have the NF cone, any lattice points inside that will be ample divisors. Okay. So the final thing I should point out here is our definition of the NF cone. It tells us that it's tightly related to the pseudo-effective cone. And this will be useful for a computation. So let me just write this as follows. If I take the NF cone is just equal to the dual of the pseudo-effective cone. So whenever you have a cone in a space, you have the dual cone in the dual space, which is just all the linear functionals that are non-negative on that cone. And so by definition, the NF cone is dual to the pseudo-effective cone under the standard pairing. So this cone is sitting in H upper 2 of X. The other cone is sitting in H lower 2 of X. And by the standard pairing, they're dual cones. So what I'd like to do now is to describe a little bit about the geometry of the corresponding cones. So let me make a general definition. So when I'm working in a cone, there's really a couple of different kinds of points on the cone. So let's say I have a cone that looks like this. So I have things in the interior, or things in the interior of a face. But I also have things that are on the minimal dimensional faces of the cone. And these things on the minimal dimensional faces, they can be characterized by the fact that you can't express them as a sum of two other elements on the cone without those elements being proportional to the original element. So let me make this a formal definition. So given a closed cone, C, so an element R in C is extremal if for any representation of R as a sum of elements D1 or D2 taken from the cone, we have that D1 and D2 actually lie in the ray generated by R. So there's no interesting ways of decomposing the extremal element as a sum of different elements. So examples are these points here, but this is not extremal. Anything in the interior of the cone is not extremal. So this is an important technique in convex geometry, and it will be crucial in the analysis that we're going to do later on. let me just make one last comment. So there are, of course, lots of cones that have tons of extremal elements. So if I take this cone, a circular cone, so I want to take the interior of this cone. Each point on the circle gives me an extremal element. Anything that's on the boundary of the cone can't be represented as non-trivially as a sum. So these are bad cones from our standpoint. You know, these circular cones are the things that we want to avoid to the extent that we can. All right. So with this said, let me describe a little bit some examples for surfaces. So one thing I'd like you to do is to actually be able to compute effective cones effectively. These examples for surfaces of effective cones. So here's the first example. But before I do this, one thing I should say. I have the monoid of effective curves. I should also mention for balance, we have a monoid of effective divisors too. So while I'm doing everything, one last definition. So I'm going to let this denote the monoid of effective divisors. And again, we have the corresponding cone of pseudo-effective divisors. And inside of here, the interior is called the cone of big divisors. So this is where things get a little pedantic. For surfaces, there's no difference. Okay? But sometimes it's important to think about them as divisors, and sometimes it's important to think about them as curves. Because the way the techniques work, it depends. So so exactly the same for surfaces, but in higher dimensions, it's actually crucial that you keep track of which is which. So, all right. So here, I'm computing either n1 of x well, these are equal for surfaces, right? And so I'm going to probably screw up and forget to put the subscript with the superscript. Hopefully it won't be too bad. So let's take x is equal to p1 cross p1. Then the Picard group is generated by the two rulings so these are just fibers of the projection maps onto the two factors. We have the intersection form. And here the pseudo-effective cone, this is just equal to sums with non-negative coefficients. So let me give another example. So let's let P2, let's take P2 blown up at 3 points. here, let's assume that P1, P2, and P3 are not collinear. So let's describe the effective cone here. Well, you can see, of course, we'll have the exceptional divisors. And I'll also have the proper transforms of the lines joined together pairs of these points. So I get 3 more of these. And this is a full effective cone. So this is, this is a cone that we can actually describe fairly explicitly. So we have, in the first case, the effective cone is just a region in space. Here, I'm going to represent it projectively. So I have 6 generators. And so the cone is the cone over this configuration. So let me tell you how to actually compute this in practice. So here's the main technique. So how to compute? And this worked well for X, say, a rational surface. It works even better for Kx minus Kx and F. In this case, it works extremely well. But whenever X is a rational surface, it works fairly well. So let's suppose we have a series of irreducible curves. And we want to show that the smallest cone generated by these curves is actually equal to the effective cone. So the first step is we produce a basis, or produce generators. We call this XC for the dual cone. Well, I shouldn't call it the dual cone at the moment because I don't know it's a dual cone. Let me erase that. Whatever cone the gamma generates. And I expect this. I expect this to be the Neff cone. If I actually have a set of generators, so let me make sure the logic is clear. We want to verify that our proposed set of generators actually gives us a whole cone. I'm sorry, I can't. The what? The dual of gamma, yes. So the second step is that, so this is the kind of thing a well-motivated computer can do. There's software for computing this effectively. So in many cases, this is not difficult to do, at least if you have sufficiently straightforward examples. The second step is for each element AI we try to express AI as a sum of the generators where the Mij's are non-negative. Another way of saying this is, so we want to check that the AIs are actually contained in the cone generated by gamma. Now, if each AI, so if we can do this, so if each AI is actually contained in the cone generated by gamma, it follows that gamma is equal to the effective cone.
Are you somehow identifying what space of this
Oh, yeah. So, I mean, yes. I'm identifying spaces with this dual. So everything is highly confusing because maybe I'm not keeping good mental hygiene. But the point is that this is a space of divisors. This is a space of curves. But I have this identification between them. So for surfaces, the way these algorithms are structured is much cleaner because we have this identification. So this is actually not so hard to see. Let me say a few words about why it's true. That's a bad decision. Let's see. I pull down both of these. All right. Probably never get that board back. So why does this work? Well, let's say we're given, let D be an arbitrary effective divisor. And let's write D as a sum of Cj plus a leftover term m, where this is effective but with no support. In gamma. So this is just the sum of all the components which are not contained in gamma. The one thing that we know is if we have a divisor which isn't contained, which has no support in gamma, it follows that when I take m and I intersect it with these Cj, we get something that's non-negative. Another way of saying this is that m is contained in the dual to gamma. So we can express m as a sum of elements. But since I can write the AIs as sums, positive sums of the CJs, it follows that by step 2, the m is actually contained in gamma. And so this tells us that D is contained in gamma as well.
Does this mean you're already starting with a full dimension?
I'm sorry?
I mean, you already have
Yes, what I want to do is if you manage to guess what the generators are, this is how you check. So if I'm given some plausible set of generators, I want to verify that they actually are the generators.
But you need to know beforehand that they span the right dimension, right? Because it seems that if I start with the empty set, then this will also follow and you end up with the wrong conclusion.
I definitely don't want to start with the empty set.
But you would find that each AI is in the span of gamma. There isn't any AI. You probably need to start with
I think I don't. If I take an empty cone or the zero cone, then the dual to the zero cone is the whole space. I don't see how I can write the whole space as linear combinations of elements in the empty set. So I think there may be technical problems, but I think, yeah, I think the empty set gets spit out of the wall. This procedure doesn't tolerate the empty set well. So the point is that I want you all to go home or go to the hostel or wherever you can find a quiet place to do some mathematics and just take a whole bunch of these examples and just compute through what the effective cones are. Okay. I guess I should give a bad example, meaning an example that doesn't have an intelligible effective cone. So this is the last example. So here's a bad example. And so let's let P1 to P8 be points in P2, chosen generally. I don't want to say exactly what I mean by this. And let's let P0 be the last space point of the pencil of cubics. Containing P1 to P8. So I have a whole bunch of cubics containing all my points. And I have this distinguished last space point. Now, let me let X be the blow up at all these points. Okay? Now, we have a whole bunch of -1 curves. But we also have a P1 elliptic fibration over P1 that comes from my pencil of cubic curves. So this is just associating to each point in the blow-up the elliptic curve that passes through that point. Now, these distinguished curves are sections. These are sections of pi. So if I represent this schematically, I guess I should number them from 0 to 8. I get a whole mess of sections. But now we can use the group law. And generally, using the group law, we get lots of sections. So I choose one of these to be 0. say, E0. Let's just set E0 to be 0 under the group law. I start applying the group law to these sections. So the thing that you need to keep in mind here is that every section of pi is necessarily a -1 curve. Just analyze. So this pencil is really given by the anti-canonical class. So all the sections have degree 1. Since they're rational, they have to have self-intersection -1. And so in this way, we find that X contains an infinite number of -1 curves. So the picture is that the cone here is not finitely generated. Because of all these -1 curves. We have an infinite number. So don't try to compute this effective cone at home. It's quite complicated. But you should start to see that there's a dichotomy between the good examples and the bad examples. The good examples where you blow up a few points, the bad examples where you blow up too many points. Okay. So what I'd like to do next is to try to describe in a more systematic way the shape of the effective cone. So let's some board space. So let me interpret, talk about extreme arrays in effective cones. And let me start with an observation, which is crucial. So let's say that X now is a smooth projective surface, and E is a -1 curve. So the result we'll need is that, well, I have N1 of X. Part of it's polyhedral. Part of it might be circular. We could have, a circular region over here. But the thing that you want to keep in mind is that the exceptional divisors are always going to be extremal. In the sense of convex geometry. So, yeah. Integers. Yes? Sure. So you'll generally have some subset of the EIs are a basis for the Picard group, and all the other -1 curves will be expressible as linear combinations.
For example, could we write E1 as an combination of the other
Oh, you mean in this example whether I could have dependency relations? Yeah. So that's why I had that qualification. I want to choose those points generically. If I choose them generically, then you're going to have a positive rank. So if I chose the points to be special, the rank could be less than you might expect. But if I choose them to be generically, I will still be able to generate an infinite number. And I think the sections will be, I think the number of independent sections will be just determined from the rank of the Picard group. So I think the number of sections is going to be the rank of the Picard group minus 1. So you can compute the rank, provided you have this genericity assumption. So why is this the case? Why do we have that these are necessarily extremal? Well, the key thing that you need to keep in mind is that let's blow down E. Now, suppose we have, well, when I blow down E, the image of the effective cone upstairs is just equal to the effective cone downstairs. Okay. Now, let's suppose that E is not extremal. So let's suppose that we had a picture like this. So here's E. We have D1. We have D2. Well, what's going to happen when I contract E? Well, if I have E equals sum D1 plus D2, D1 and D2 pseudo-effective, but not contained in the array spanned by E, then if I push down E, I get this relation. So if this is the picture in X, then in Y, I get a picture like this. So this is in X. This is in Y. So D1 and D2 are on a line through the origin in other directions, but this is impossible because a divisor and its minus can't both be effective. So we can't have both D and minus D effective, or even pseudo-effective, if D is not equal to 0. So well, so I should have said that, in fact, when I blow this down, the Picard group of X is just equal to the Picard group of Y plus the rank 1 lattice spanned by E. So the only things that can go to 0 under beta are the things that are proportional to E. But I'm assuming here that D1 and D2 are not proportional to E, so they don't go to 0. So with this in mind, I'm going to give you, without proof, a complete description of all the extremal elements of the cone. So this is called Morey's cone theorem. So let me draw a picture. I want to understand the cone of effective curves. Now, I have a line here, which is the orthogonal subspace to kx, the things that intersect with 0 in kx. And then I have the locus of D where kx D is negative. So this is a half plane. Okay? So things behave well below the line and behave badly above the line. That's the content of the theorem. So let me state it more formally. So let's say that X is smooth projective surface. With canonical class K of X and H ample. What I'd like to do is I'd like to describe the effective cone, but only the parts of it where K plus epsilon, epsilon is a positive number, is less than or equal to 0. So this is equal to So here what I'm doing is I'm kind of pushing off away from this line. So this is kx plus epsilon h perp. So this is another hyperplane section. So then the claim is that this is rational, this cone is rational polyhedral. And so generated by a finite number of extremal elements. RI. So the picture is that in this region, the cone is going to look like this, where each of these is a rationally defined class. So we get a finiteness theorem. So one corollary, which I should state right away, is that if X is del Pezzo, it implies that this is finitely generated. Because, I mean, everything is kx negative. Okay. So the picture is that you could have really bad stuff going on up here. It could even be circular in the top part of the picture. But in the bottom part, I can control it. Now, where are the exceptional curves? Where are the -1 curves? Well, let me just remind you that every -1 curve is contained in the k plus epsilon h less than or equal to 0 region for epsilon sufficiently small. So all the -1 curves here are on the bottom part of the diagram. So this is a structural result. So all of the examples I did fit into the structural result. If you look at the bad example up there, I chose it in such a way so that the canonical class is not ample, but just barely not ample. As soon as the canonical class is not ample, the structure of the cone goes to hell. Everything is extremely complicated. Okay. So what else should I mention about this? Well, if all we had was this description in terms of convex geometry, this result wouldn't be so useful. But in fact, we can say much more about these rays. So this is the second part. So this is a modern version of the Castelnuovo criterion. Castelnuovo's contractibility criterion fits into this picture. So let's say that Ri is an extremal ray. By this I mean its extremal element with kxr equals 0. So examples are -1 curves. Right? We saw that -1 curves are extremal here. They're extremal in the sense of convex geometry, and they're definitely kx negative. So there exists a contraction morphism phi from x to y to a smooth projective variety with, well, phi r equals a point. And because we have this extremal element, I can cook this up in such a way that I only contract R. So let me spell out precisely what this means. So this contraction has relative Picard number 1. There's two ways of thinking about this. One way of saying this is that the rank of the Picard group of X is equal to the rank of the Picard group of Y plus 1. Another way of thinking about this is that every curve C contracted by phi is proportional to our extremal ray. So this is a general structure of the contractions. Now, what I'd like to do is I'd like to spend a little bit of time reading off what this tells us. So what can happen here? So there's a few possibilities. So what can we say about, well, the first case, let's consider what happens when r squared is less than 0. Well, then, it follows by our proposition from last time that r is a -1 curve, and phi from x to y is just a standard blowdown map. So this is what happens in the first case. But there's no guarantee that r squared has to be less than 0. We could have r squared equals 0. Now, what this tells us, well, is that r is still a rational curve, but the dimension of the linear series containing r is positive by Riemann-Roch. And so the induced morphism contracts all these curves. So these are all contracted. And so here we have that it follows that, so this is a smooth conic bundle over a curve y. In the last case, where r squared is actually positive, we get that r moves in a large dimensional linear series. And so here we actually get that y is equal to a point and x is equal to P2. So this is the general structure for the contractions. And so you should really see this as the fundamental result, not the Castelnuovo criterion. This is going to behave much better when we pass to non-closed fields. So in the minuscule amount of time I have left, which I have only on my watch, not on the official clock, but I have 1 minute left. By way of application, let me tell you about all del Pezzo surfaces. So if x is del Pezzo, then either x is isomorphic to P1 cross P1, or x is isomorphic to a blow-up at some number of points in P2 where n is less than or equal to 8, and these are chosen in suitably general position. Now, how do I interpret this in terms of the contraction theorem? Well, the one thing that you can see for a Del-Petzel surface is, so there are lots of curves to contract. And so what we should do is we should contract the -1 curves first. So step 1, let's take the -1 curves. That is those with r squared. And so this gets us to the situation where x is a minimal Del-Petzel surface. And then, so step 2, we have two possibilities. Either x over P1 is a conic bundle. So x is isomorphic to some Hertzsprung surface. In this case, the only possibilities that are Del-Petzel are F0 or F1. I guess I should tell you that Fn is this projective bundle over P1. Or we have x is equal to P2. So using the contraction theorem, it gives us a fairly transparent way to analyze the Del-Petzel surfaces. And I apologize, I don't have time to explain that. But I'll be happy to explain it to anyone.